So welcome to new lecture on stiffness matrix method. So today we are going to discuss a problem on continuous beam. So S beam A, B, C span is given. So we have two span A, B and B, C. So it's a continuous beam. Loadings are given. So how we will analyze or how we will solve this problem using stiffness method. So we have seen how we can solve the same question using slope deflection method, flexibility method, and now we are going to see how we can solve using stiffness method. The first step is fixed end moments. So span AB I am considered and keeping both the end fixed. That's how we find out the fixed end moments. We keep all the end fixed. So AB span, both ends are fixed. I apply the UDL load 5 kilonewton per meter. So the formula for the fixed end moment is WL square by 2L for the case of a UDL, right? For the case of a UDL, the formula is WL square by 12 in the direction as shown below. So anti-clockwise is taken as negative, hence this will be negative, and clockwise is taken as positive. Calculating, I will get 10.416 as MFAB, that is minus sign. And calculating MFBA, I get as positive 10.416 kilonewton meter acting as fixed end moment in the span AB. Now I am focusing on span BC. The loading is shown as 1 meter and 3 meters. The 50 kilonewton load is distributed as 1 meter and 3 meter apart. So the 1 meter will be my A distance and 3 meter will be my B distance. The formula to find out the fixed end moment is WA B square by L square when checking from B to C. I am looking from B to C, then I have to measure as W into A into then B square by L square. And when I am checking from C to B, that is from C to B, I will take it as W, that is 50 kilonewton is a concentrated load, into B into A square by L square. L is a total length, that is shown MFCB. So minus 50 into 3 into 1 square by 4 square is MFCB, and MFBC is minus 50 into 1 into 3 square by 4 square. Calculating, we get two values. Now our first step is completed, a fixed end moment. And next step is calculating equivalent joint load, which is a very important step. That is, the meaning of equivalent joint load is that in matrix method, we will not calculate the load as UDL or a concentrated load, but we will focus it as a load acting on the joints. Here, what are the joints we have? How many joints do we have? A is a joint, B is a joint, and C is a joint. But the load is acting as a UDL, right? 5 kilonewton per meter is a UDL. So I have to convert this UDL load into some load that is acting on the joints. That means equivalent load acting on the joints. Okay? 5 kilonewton per meter നോട് ഈക്വൽ ആയിട്ടുള്ള ലോഡ് ഞാൻ ജോയിൻസിലേക്ക് അപ്ലൈ ചെയ്യുന്നു. അപ്പോൾ 5 kilonewton per meter അതേ ഇഫക്റ്റ് എയും പിയും ജോയിൻസിൽ കിട്ടില്ലേ, അതാണ് കൺവേർട്ടിംഗ് 5 kilonewton per meter into joint loads. Similarly, I convert the 50 kilonewton concentrated load into two joint loads, that is load at B and load at C. So how can we find out that? For which we will use fixed end moment. That is, what is fixed end moment basically? Fixed end moment is a load that will resist the applied load, right? Or it is a moment that will resist the applied load. It is equal to the applied load, it's right. Applied load in opposite ചെയ്യുന്ന ഒരു equal and opposite moment തന്നെയാണ് the fixed end moment. So if we change the sign of the fixed end moment, that will become the direction of the applied load, right? So that is nothing but low applied load in terms of joint loads, right? So we are converting the fixed end moments into equivalent joint load acting as an applied load on the joints. That's the idea. ഫിക്സഡ് എൻഡ് മൊമെന്റ് എന്ന് പറയുന്നത് റെസിസ്റ്റ് ചെയ്യുന്ന ലോഡാണ്, പക്ഷേ നമുക്ക് വേണ്ടത് ജോയിന്റിൽ ആക്ട് ചെയ്യുന്ന എക്സ്റ്റേണൽ ലോഡാണ്. അതാണ് ഈക്വലന്റ് ജോയിന്റ് ലോഡ്. അത് കിട്ടണമെങ്കിൽ ഫിക്സഡ് എൻഡ് മൊമെന്റിന് എന്ത് ചെയ്താൽ മതി? തിരിച്ചിട്ടാൽ മതി, ഡയറക്ഷൻ മാറ്റി കൊടുത്താൽ മതി. സോ അറ്റ് ജോയിന്റ് എ ഇറ്റ് ഈസ് എ ഫിക്സഡ് എൻഡ്. സോ there is already a resistance against the moment. So this 10.1416 need not be considered in equivalent joint load. So here nothing is being given. And at the joint B, it is actually a roller support. So a moment is allowed at that point. So a moment will exist. How will be its direction? Here, the fixed end moments are 10.416 and 28.126. We have to get the larger value and apply the fixed end moment will be in the direction of the larger load. Here, 28.125 minus 10.416, I will get 17.709 as this load, right? As a anti-clockwise load. That is a fixed end moment. Now I change the sign of this load as shown in this figure. Okay, 17.709 kilonewton meter is an equivalent joint that has been obtained by changing the sign of the fixed end moment. Okay, now go to joint C. There is a fixed end moment of 9.375 that is acting in clockwise direction. I convert it into equivalent joint load. It will be in anti-clockwise direction. Is there any other load acting at a joint C? There is also an applied load of 10 kilonewton per meter acting at that joint. So you have to add that load also here in the same direction as shown in the question. That is 10 kilonewton per meter. 10 kilonewton meter is acting in clockwise direction and 9.375 is acting in anti-clockwise direction, and its resultant will be 0.625 acting in the larger direction, that is in clockwise direction. That is by equivalent joint load. Yes, as shown in figure. These two are my equivalent joint load. So these are the two load acting in the structure. So two loads are acting. So what will be our system coordinate? The point at which or the direction at which the load is being acting is our system coordinate. First system coordinate will be this one and second system coordinate will be this one. That is two moments. Okay, we name it as R1 and R2 in clockwise direction. So while defining system coordinates, we can always give it in clockwise direction. And if this one is anti-clockwise, we can change this side. That's how. Here both are in clockwise. So I'll write the load matrix, P matrix or capital letter R matrix as 17.709 and 0.625 representing the two load positions. Okay. Now another step, next step is element coordinates. That is, we have two span, we split into two different spans, that is AB and BC. That is 1 and 2. We will have 1 dash, 2 dash, 3 dash, 4 dash. And we have to find the K assembled. Assembled matrix will be sum of first matrix and second matrix, that is K1 and K2. K1 is 2 EI by L, 2, 1, 1, 2. That we have derived the stiffness matrix for a beam element. So length is given. Length is 5 meters. So 2 EI by 5 into 2, 1, 1, 2. K2 is KBC, that is length is 4 meters, 2 EI by 4, 2, 1, 1, 2. You can as a common, you can take 2 EI common outside. So I took 2 EI common outside. Wrote balance terms as 2 by 5, 1 by 5, 1 by 5, and 2 by 5. These are zero terms. This is my KBC, 2 by 4, 1 by 4, 1 by 4, 2 by 4. This is a 4 by 4 matrix for which we need a calculator to solve. If you have a 4 by 4 calculator, it would be easier. So this is my element stiffness matrix. Next step is displacement transformation matrix, A matrix. So first condition is apply unit displacement, that is unit system displacement at a first system coordinate. So first system coordinate is a rotation R1 or a moment. So I apply theta equal to 1, that is rotation equal to 1, slope equal to 1 at point B. So that is theta equal to 1 here, theta equal to 1 here. This one, clockwise moment, clockwise bending is shown as I explained in my previous video. Here it is a fixed end, hence theta equal to 0. Here also fixed end, theta equal to 0. And then second system coordinate, I apply unit displacement at my second system coordinate, R2 equal to 1. Here, just a system coordinate, clockwise direction, theta equal to 1 at that point. All other points, we have theta equal to 0, theta equal to 0, theta equal to 0, because we assume all other end as fixed. That's why even though this is roller, I assume here it as fixed because I apply unit displacement at second system coordinate assuming all other ends are fixed. Now I write the A matrix as 0, 1, 1, 0, 0, 0, 0, 1. And next, only up to this much there is a complexity. After which you can just substitute in calculator and then find the answer. Step 6 is system stiffness matrix K. Capital letter K. Formula is A transpose dot K dot A. So I took the transpose of A. You know A is given here 0, 1, 1, 0, 0, 0, 0, 1. How we'll take the transpose? Interchange the row and column. So this column will become the row here. So 0, 1, 1, 0. And this column will become the row here 0, 0, 0, 1. That is my A transpose into 2EI taken outside. This is my small letter k element stiffness matrix into A. So you can use substitute this one directly in calculator. That is matrix A. You can define this as matrix A, this as matrix B, and this as matrix C in calculator. You will directly get this value. This is my capital letter K. Okay. While defining, you can also define matrix D along with that. Before finding the calculation, you can define matrix D in calculator as my load matrix. Okay, that is P matrix also you can define before solving the problem. So next step is system displacement R matrix. So what we can do, you will calculate matrix A into B into C, you will get the K value, directly take the K inverse in calculator, and then multiply this answer with the load matrix P. So that's why I told you to define this load matrix earlier, so that you can directly substitute this value and find the R value. Okay, this R value, that is my system displacement. You will get this answer. And next step is element displacement. Q value, that is A dot R. You can just write this as like that and go to the step 9, that is element force. Capital letter Q is equal to K dot Q, where Q is equal to A dot R. Okay, this, so what can do, we can substitute the value of this all three cases and then directly substitute in calculator, rather than finding Q and then giving it here. You can directly give the value of K, small letter A, and a small letter R. Here this K represents element stiffness matrix, that 4 by 4 matrix. Okay, element stiffness matrix, not the system stiffness matrix. Okay, then substituting, you will get a capital letter Q, which is called the element forces. We get four values, then add it with the fixed end moments obtained at each joint, that is A, that is AB, BA, BC, and CB. Then you will get the final end moments. This is how we solve this problem for a continuous speed. Thank you.